Hope it is visible.
Yeah, perfectly all right, sir.
Yes,
Everything
please,
is
please
good.
go ahead. Go ahead.
My presentation is sort of a general, like the first part we look at, because the geosynthetics, the significant use started maybe around 30 years ago. So over the 30 years, sort of summary, like a very, very broad overview, like what has happened, what's the story about. Then we will look at 5 applications in detail, slightly more detail, like reinforced soil walls, like these 5 applications in detail. So if you look at a broad overview, at a glance, if you look at here I am listed the major achievements. Like first is the impressive growth in indigenous manufacturing. Like today we manufacture a lot of products in India, like compared to earlier, like because earlier we used to import most of the products. Then there is a appreciable use in many areas, like reinforced soil structures, landfills, erosion control, coastal protection, ground improvement, etc. Then a high level of indigenization, like of course manufacturing I mentioned earlier. Then we developed a lot of expertise, like design and construction expertise. Then we have our own standards, like standard specifications, etc. Because if you look at maybe situations of like 20 years back, we used to have everything like products, expertise, designs used to come from abroad, and even the installation experts, they had to come from abroad actually. But now, like we are able to do most of the things ourselves. Like then the single most important development I would say is the huge growth in reinforced soil walls. So this we will see later on also. Then the construction of several landmark structures. Like today we have constructed reinforced soil structures of say 70 or 80 meter high. Like I recall like something like in 1998, we were working on a project in Mumbai. We had to construct a reinforced soil wall of something like 12 meter height. So at that time, it was one of the highest structures in India. And people did not have that kind of confidence, like, will it really stand? Like we are putting plastic meshes into the soil, will it hold? So the consultant had put a condition like, I will approve the design only in one case. You'll have to call. At that time, our principal was from UK, Tensor UK. The person from UK has to come. I will ask him like whether he has constructed a structure of such height in UK. Only if he says, yes, I will approve. Then we called a person from there. He said, yes, sir, we have constructed 15 meters high structure in UK. But today, like we are confident about like 50 meter or even 100 meter, like we have the confidence. At the same time, we have a lot of limitations also. Like one is most of the manufacturing facilities are located like north or west like that. In the distribution channels, like suppose we want to buy a product like a small quantity, it is still difficult actually, because most of the time the product has to be dispatched from the factory. Whereas something like a brick, cement or steel, we can go to the neighborhood shop and any quantity we can buy. But geosynthetics, it's not like that. Still, it is difficult. And still limited awareness, limited use in many applications like that. And expertise is still limited within a small community of like a geosynthetic specialist. Like whereas in the case of a RCC design expertise, like a lot of civil engineers have that expertise. And still there are many failures like that. Then like we are constructing a significant number of structures, but we are not monitoring, like we are not quantifying the performance. That way we are lacking very much behind. Then I mentioned the indigenous manufacturing. Here I have tried to list like various products and how many manufacturers are there in India. You can see we are manufacturing most of the products today. Maybe only one product that we have, the product known as the turf reinforcement mat, that probably nobody is manufacturing in India. Apart from that, all of the products we are manufacturing and in good quality also. The quality is of international standards and the capacity is also huge, like many manufacturers. And in fact, many of the manufacturers are exporting to many countries. Now, if you look at the ecosystem, like to use the geosynthetics, what kind of environment, what kind of facilities support we need. So I have listed the various aspects. Like in some, we have made huge progress, especially in manufacturing, like the products are manufactured. Whereas, as you mentioned, the distribution, we are lagging behind. Actually. So if I want to buy something like a 500 square meters of non-woven geotextiles, it will be difficult. Actually. Then awareness and acceptance, it's growing, but still a lot to go. So education sometimes, like we have to see. Good thing is, like if you are teaching the students in BTech in the materials course about geosynthetics, it will go a long way. Like, see, if somebody has learned it in the college, like that, it remains in his mind. He may forget what he has learned, but at least geosynthetics, it's an accepted material that impression will be in his mind. All these areas, we had made a lot of improvement, but much more improvements are required. And research and development, we are doing a lot of research, but then does it really help the practice? That we have to think about. Then one important aspect is the design, because if you want to use, we have to have confidence that it will work. Actually, so the performance has to be predicted, which is done by the design. So here, like if the corner used to list 3 methods. Eurocode lists 4 methods like that. So I have given a simple classification. Right? So is like reinforced soil structures, walls, slopes, and embankments. We use calculation methods, are well-established methods are there. There is absolutely no issue. Can be done confidently. Then other applications like filters, drains, geomembrane laners, like subgrade stabilization, paving fabrics, etc. We go by specifications like that. Those different standards or guidelines give what type of products to use. So generally we follow that. This is also good, like it is an accepted practice. Like everywhere we cannot do a design by calculation, it will not be worthwhile also. Important is like the specifications the prescriptions has to be reasonable, and it has to be updated in line with our experience. If you look at ground improvement using PVD, we use calculations. At the same time, we use an observational method. Because there are many assumptions involved in the design, especially the coefficient of consolidation. So it has to be verified by monitoring settlements and core pressures during construction. It's very important. So granular bases and subbases, it is because pavement design, railway track design, it's highly empirical. So we have some calculations at the same time, a lot of testing also. Then there are some inherent difficulties in designing with geosynthetics. See, first of all, like if you take filtration, like in principle methods are there, like the formulas there, like various equations are available. Actually, because if you consider the variability of soils, like within a 100-meter stretch, the particle size, gradation, it varies too much actually. So sometimes it is not worthwhile. So probably that is why we go for a specification-based approach. Coming to drainage, again, in principle, it may be possible, but sometimes you have to deal with transient flow and saturated flow. It is very complex. Doing a practical design may be very complex. So sometimes, again, we go by a specifications or experience-based approach. And payments and track widths, it's highly empirical. Actually. So slowly we are moving towards mechanistic, empiristic design. But then empiricism means we have to go with experience. So the conventional, we have a lot of experience, but with geosynthetic, we have less experience. And coming to coastal protection, bank protection, here we have very complex, like a soil structure, water interactions. The phenomena is very, very complex. So developing a rational design method is not easy. We may do a model and do a design, but how much it really reflects the actual situation, it remains to be seen. And again, there are some inherent limitations. See, first of all, geosynthetic reinforced layers are non-homogeneous and anisotropic. Then one important aspect is it's very difficult to conduct elemental test. That means, like suppose to give a comparison, if it is a chemical stabilizer, you can mix with the soil, prepare specimens, do a track shill or a simple shear test. From that, you can derive the constitutive parameters directly. Whereas in the case of reinforced soil, this is very difficult. So we have to sort of back calculate the parameters. And small scale lab models have very limitations. And if you do full-scale models, then the cost, the time, and again, because of the variability in ground and hydraulic environmental conditions, to replicate it to other situations may be difficult. So coming to the reinforced soil walls, like as I mentioned, this is one of the huge success stories. So I tried to estimate what is the current demand, talking to industry colleagues. So it says it should be around 50 lakh square meters of wall face area per year. And it could go up to something like 100 lakhs square meters per year like, in a few years' time. It's a huge, huge quantity. It's predominantly in the highways. Then the indigenously manufactured geosynthetic reinforcement like knitted and coated polyester geogrids, polyester straps, and concrete panel and block system is widely used. Metallic reinforcement is rarely used, mainly because of the cost criteria. Then one significant development is the use of the geogrid strips actually in India. Because earlier we used to have almost 90 to 100% coverage of reinforcement. Now what people are doing, they cut into narrow strips of 200 to 300 mm width and double layer. Like that means same strip comes, loops around this and go back. Like that. Different type of connection. And again, mainly it has come from cost to optimize the cost actually. Then a lot of experimentation in the connections. Then one main challenge is to get the good quality granular fill because we need a fill with less than 15% fines, which is becoming very, very difficult to get at. So in future, this is going to be the biggest challenge we are going to face. And we also have a number of failures. So failures coming to see, actually, we hear a lot of messages like failure happened here. But the problem is we don't have any authentic figures like what is the frequency, how many failures actually. And is the frequency of failure of reinforced soil structures more than conventional? We have no idea because we hear about many failures of conventional structures also. So majority are connection failures, maybe 90%. The facing, the connection breaks and the facing collapses. All this excessive bulging is a problem. Poor quality of blocks and damages of panels, etc. Then poor quality of fill, it's a frequent problem because sometimes the specifications are only on paper. On the ground, it's an entirely different situation. Then detailing, excessive differential settlement, and few cases foundation failures also. And if you look at what are the underlying causes, the most important is intense competition. The competition is so severe, like you're being forced to find ways to reduce the cost. Ultimately, sometimes quality has to be compromised. And weak regulatory mechanisms, like the codes, how the codes are implemented like that. Again, we need to do a lot. Huge volume of work, a lot of work. So even uncompetent agencies are given work like that. And sometimes there are a lot of delays. If a project is actually 3 years, like a lot of time goes, land acquisition, environmental clearance, issues with the DPR, then the actual time for construction is very limited. So within that time, the contractor has to rush and complete this job. So sometimes compaction is not done properly. We know in India, that work practice is very much behind. We don't follow a scientific approach. So the way forward, actually, the one option is the NHAI, they should bring a status report, like because the major volume of work is there. What are the experience? What are the failures? What are the learnings? Like that will be very helpful. Then we have to strengthen the regulatory mechanisms. We need for government funding actually, like because compared to FSWA, like they fund a lot of research, a lot of reports. Whereas in India, I don't see it happening. Training. We need more labs, then proper forestry investigations, and monitoring and performance evaluation. This is a very, very important area, but we are ignoring it. Then we have to expand to the other sectors also. Then another important application is stabilization of granular subbase and base. So we need a huge quantity of granular material. Like if you want to keep up the highway construction activity, it's not available. Sometimes the good quality is not available. So sustainability is a problem. So one option is, can we reduce the granular thickness using granular surface, geosynthetic reinforcement? Or can we use lower quality materials? So, like we are having these materials, IRC as having a guideline. There is a BA standard for products. Then we have better facilities. And also nowadays project execution is in PPP, EPC or hybrid mode, which encourages innovation. So conditions are favorable to use, but then we have certain challenges actually, how to incorporate in this design. So the IRC has a guideline how to design. It is based on the LCR approach or the modulus improvement factor. So we have either a layer coefficient ratio, that means it is a quantitative measure of how much the geosynthetic improves the performance, or a modulus improvement factor like that, which has to be experimentally determined. So now these factors depends on a number of factors actually, like the characteristics of subgrade, the thickness of each layer, properties of each layer, then the location of geosynthetics in various. So each factor may influence LCR and the modulus improvement factor. To determine, we have to conduct either we can go for a cyclic load test or a field trafficking test. Because the main difficulty is we have to test so many combinations actually. So mainly, like the challenge is in the determination of the LCR or the modulus improvement factor. So whether we should go for a lab or field test, then how many minimum number of cycles we have to do, how to interpret like that, all these are complications actually. So, and at the same time, geosynthetics will have to compete with other techniques like chemical stabilization, which I mentioned, testing is easier. So unless we get some support from the government, this may be difficult. So if you have a national program of evaluation, like which can be, the cost can be shared by the manufacturers and if possibly partly funded by the government, but coordinated by a central agency, then the results will be sort of consistent and it can be accepted by. In track, but also the same situation comes actually. And here it is more difficult than highways because the track bed design is much more empirical actually compared to highways, and the expertise is mostly limited to railways actually. So here also, unless the railways or RDSO takes an initiative, it may be difficult. So the UK Network Rail has a design method, like they have their own design methods. Like if you have a geogrid reinforcement, there is one value of support modulus. Without, there is another support modulus. So they have charts. So depending on the type of subgrade, we can go to these charts. So if it is without geogrid, it will be this much thickness. If it is with geogrid, this much, something like a 200 mm savings. So probably Indian Railways also can think of developing such design methods. Then another issue we have is the coastal protection. So we have a huge problem actually. And the conventional technique is using stone actually, which is again difficult to get. So the alternative explored is sand-filled geotextile tubes. See, also using tubes. So at one time, this was a very promising technique. Like people had a lot of belief in this. This was supposed to be a sort of a magical solution to the coastal protection problem. Several such sea walls were constructed. Unfortunately, we had problems. Many performed satisfactorily. At the same time, there were many failures also. So I have shown some paper cuttings here. So if you look at the reasons, there are many reasons actually, because exposed geotextile tubes are prone to UV degradation, fire, vandalism. Then if the geotextile is protected with the soil cover, it has good durability. But during a storm surge, that may be washed off. Again, we'll have to put it back actually. But in government projects, this frequent maintenance, again, it's a problem actually. All this wave loading, abrasion, the lack of expertise, then the very concept of seawall itself is being questioned actually, whether it is the appropriate solution. So the way forward is here is we have to critically evaluate both success and failures, learn from that, where geotextile works like that. Sometimes the submerged breakwaters or reefs, it could be a good option. Focus on those areas. And another application is the jute and coir geotextiles. See, normally these are biodegradable. They last maybe like a 6 months, 1 year, 2 years like that. Then they degrade actually. Their traditional application is in erosion control. So where biodegradability is not an issue, it's an advantage. But recently, like efforts are being made to promote this in other areas like roads and other applications. So they are trying to enhance durability using treatments. But at the same time, there is another argument to justify the use of natural geotextiles in applications which require longer life. They say the role of the geotextile is to act as a change agent to facilitate formation of a filter cake or promote consolidation of soils. Then this happens in a few seasons. After that, the geotextile has no role to play, and therefore biodegradability is not an issue. I have just 2 more slides only. I'll finish fast.
Yeah, fine. Thank you.
So one argument is like once the filter cake forms, the role of the geotextile is not relevant. So what is a filter cake actually? So normally, like we have a course like a revetment or a ballast or something like that. Then we have soil with a lot of fines. In between, we have a geotextile filter. So now geotextile may have openings, maybe 75 microns, 100 microns. So particles finer than that will wash through this. The coastal particles will be retained behind that. Then these will in turn retain particles smaller than this. So over a period of time, a graded filter zone will form behind the geotextile. So this may happen in, we don't know, maybe 6 months, 2 years, doesn't matter. So one idea proposed is, see, once this natural filter zone is formed, then the geotextile has no role to play. So we can use biodegradable geotextiles. But my question is, if assume that geotextile are degraded actually, but still, see, if these particles, even these larger particles are much smaller compared to this, the voids in this can pass through actually like that. So the geotextile filter, it does not become redundant actually. It is required. The only advantages of natural filter zone is the geotextile has to retain only the larger particles. That's all. Like so, that we take it to this, but does not mean that the geotextile is redundant after the natural filter zone is formed. Another application is a lot of nowadays, especially in the rural roads, a lot of jute geotextiles and fur geotextiles are being promoted. So, like, how does the geosynthetic enhance the pavement performance? So, I have compared like normal geosynthetics in the technical literature. We are familiar like separation, lateral restraint, subgrade restraint, tension membrane support. This is the way we explain the contribution of the geosynthetics. When you come to coherent jute geotextiles, it's a entirely different narrative actually. So here it says geotextiles facilitate consolidation. Then the subgrade improves in strength, CBR increases, and sometimes the field measurements show CBR increase of 2, even up to 5, 7 times increase. So as the subgrade with the time, 1 or 2 years, subgrade becomes stronger, the coherent geotextile degrades. So there is no problem as such. So I find issue with these arguments like that. So first of all, like the subgrade will be compacted with heavy rollers. So after that, only the pavement is constructed. So the weight of the pavement, like the granular layers and asphalt, the weight may not induce any consolidation because subgrade will be almost like over consolidated under the rollers. So any consolidation may be minimum like that. Then the stresses, like we can understand the consolidation below an embankment actually, but the traffic stresses are not like that. The stress path is not like that actually. So we cannot compare those situations and say the soil consolidates. Then how does the geotextile facilitate consolidation? It doesn't change anything. At best, it acts as a filter only. So we cannot say that the geotextile accelerates the consolidation. And sometimes it's claimed geotextile absorb water. So is there a wicking action? So is this process irreversible? Then a lot of field measurement, there are a lot of papers showing huge increase of CBR in the subgrade where geotextiles are used. So, but CBR is related to the undrained shear strength. So if there is an increase means there has to be a big increase in the undrained shear strength. Again, undrained shear strength is related to the effective stress actually. Because if you know the vertical effective stress, we can calculate the undrained shear strength. So in a pavement, how does the vertical stress increase? Then another question is, if significant consolidation occurs under the traffic loads, doesn't that mean the routing has occurred and the payment has failed? So I find a lot of problems with these arguments like that. So I request experts to have a relook at these two hypotheses. So to conclude, India has made a lot of achievements in areas, but a lot of aspects we have to really improve further. In the case of rainfall soil, we have seen big success in terms of volume, but quality issues are there. Then it is mostly restricted to highways. Then availability of fill is a major issue, and how we are going to handle that remains to be seen. Because even with good quality fill, we have so many problems. So when we use poor quality fill, what will happen? It's a scary situation. Then stabilization of unbound aggregates in roads and railway tracks. It's important. It's a national problem because from the issue of sustainability, this is a very important application, and probably it requires a lot of support from the government. Geotextile tubes, coastal protection, we have to learn from our experience, learn from the failures, and optimize the designs. Then coming to coherent jute geotextiles, these are excellent materials, but then when we try to push it for other applications, we have to be careful actually, and we have to apply a sound engineering approach. So with that, I conclude. I thank the organizers once again, and I thank the panel and the delegates.